So we're going to take your exponential function and we're going to actually graph it with a reflection. Here's your exponential function. For your y equals x, we're going to actually graph this as a reflection in your y equals x. There's your log. That's a log function. And all the attributes of your exponents, anything that was x, like a domain, will go to y, like the range. They'll interchange as well. Now, before we start this, just so that you kind of have a better feeling for your logs work in base 10. And my favorite line that I use for everything is log equals exponent. Whenever we're going to flip from an exponent to a log to an exponent, we use log equals exponent. Now, what this comes from is your base 10 numbers. So if I take the log of 1,000, my exponent is where my scientific number comes from. I have to move this 3 decimals. So my log of 1,000 in base 10, because everything's in base 10, is my exponent, 3. My log of 100 would be what? Make this a scientific notation number. What's the exponent? 2. So my log of 100 would be 2. My log, and so forth. If I gave you 10,000, you'd move it again. Now, all of your logs in your calculator work in base 10 because that's where that log statement is, right here. Right here. So if I take the log of 100, I'm in base 10. It's my exponent. Log is an exponent. So in base 10, my log of 100 is 2. My log of 1,000, 3. My log of 0, can't do a log of 0. We're gonna find that's where my restriction is. Can't do a log of 0. Can't do a log of a negative number. Look where my graph goes. Look where my domain is. From 0 to infinity. That's where my domain is. It's the complete opposite of your exponent. However, I can get the log of 0.01. What is the log of 0.01? Without putting it in your calcs. Think where your exponent is. -2. You're all moving it over. Your log is -2. Now that's what you come out with. That's what your range comes out in between. So your log of 0.01, because it's still greater than 0, gives me a -2. And isn't my range all real numbers now for my logs? Right? So does this kind of make a little bit of sense where our logs come from? Okay. Now, one of the things we usually do is, until we learn our log rules, is we take the logs and we interchange your x and your y from your exponential or from your logs, where we're going, and we make a log statement, or we bring the log statement back to an exponential statement. And I don't know if you remember from Algebra 2, changing the base in your calculator. Some of you have, if you have the 84s, you have a change of base. I'm not sure if my calculator has it. Under math, you have a change of base under the summation. I don't have it. The 83s definitely don't have it. But if you go to math, you get the summation formula, and underneath it says change of base. It actually lets you put a different base into your calculator. Your line is through. If the line is through, that means they reset these calculators and they didn't allow them to use it. I have to reset some of them. The 83 also doesn't have the change of base. But we can physically go change the base of any log, and we'll do that next week. Today, I just want to kind of get you to see graphically how we go from an exponential function to a logarithmic function. Now, one of the key things when you do a reflection over the line y equals x is you interchange your x and your y. And your domain interchanges with your range interchanges with your domain. Your asymptotes will have to interchange because your y equal will now be an x equal. It will all make sense when we graph this. Now, when we convert an exponential to a log, the easiest way is interchange first, and then set this up, and it probably looks easier if we put this in a number here. Interchange these guys first, and set this up, log equals exponent. This is the easiest way to remember how to flip them back and forth. The base of your log is the same as the base of your exponential function. So this base is 2, so my base of my log will be 2. Somebody's phone. So what's your exponent on this guy? What's your exponent? Y. So we're going to be equal to y, and then your x goes here. Okay, so we can take that and we can flip it back to a log. We can go back and forth to logs and exponents. Now there's another way too, like if I do this, but let's give it a nicer example here. The log base 3 of x equals 2. To get the log back to an exponent, you go like this. The base of your log is 3. So the base of my exponent is 3. My exponent is equal to what? What's over here? Just line it up. 2 equals x. So what you couldn't solve over here, can you solve over here as an exponential problem? And what is 3 squared? 9. Now, to check this, if your calculator has the change of base, it allows you to put this base in. It allows you to put the 9 in. If it doesn't have change of base, this is how simple it is. We draw a line like this. The one that sits below, we put below. Log, we just changed it to base 10. The one that's above, we leave above. We just changed that to base 10. Now that I can put in my calculator. I can put in my calculator log 9 divided by log 3. And it will give me 2. See it? If you have the change of base, it works really nice. And I'll try to fix these calculators. Some of them I noticed have it. The other ones have the lines through it. Somebody disabled that app. But now the Regions allows you to use this change of base formula. It allows you to use the summation too. So why they're still Xing them out, I don't know. So if you want to change back and forth through this, a good way to do it is log equals exponent. This one we can solve either way. We can change the base. The one on top stays on top. The one on the bottom stays on the bottom. You can put that in your calculator. Or log equals exponent. The base of your log is 2. Your exponent is y equals 32. And 2 raised to what power will give you 32? 5. Which is exactly what this one will give you. 5. So we're going to have a number of ways to find these. The reason we use logs mostly, science uses a lot of logs. For us, we use logs because we have variables in your exponent. Just like the things that we just got done doing, we had to graph them. To solve them algebraically, we have to be able to bring down that exponent. The power rule will bring down your exponent. So we use logs in our applications for one of those reasons. But I don't, has anybody used these in science and physics? Does physics use logs? No? Ken? Nobody uses logs? I thought one of the scientists did. No? Okay. Alright. Now, I'm going to pass this up for a minute. We're going to come back to that next week. Today I want to get you to go from an exponential function to a logarithmic function. But I want you to see all the characteristics of this. Now, this is what we did last week. We graphed your exponential curves. They graph like this, right? We said it has a domain of all real numbers. We said it had a range from 0 to infinity. It has a y-intercept of 0, 1, and it has an asymptote of y equals 0. Didn't we find that, right? So if we put this in your y1, we're going to get 2 to the negative 1. What does that negative exponent do? It turns it positive, but it takes the reciprocal. It inverts it. What does 2 to the 0 do? 1. 2 to the 1. 2 squared. 4. Now, your rule is, because it's a reflection, every xy is going to swap to yx. So rather than graph this, we're going to take your table and we're going to use this rule. We're going to switch these, interchange them. So 1/2, negative 1, 1, 0, 2, 1, and I'm missing a little box. 4, 2. When you graph this, your point that you're going to look at is the point of your 1, 0. This is what's going to be in common in all of these guys, is your x-intercept. Because doesn't the y become the x? So we're interchanging. So now this point over here will become this point here. Okay, now, let's use the whole concept of x and y interchanging. Your domain is an x value. It's going to change to your y value. So your range will be negative infinity to infinity. Your y value was your range. That will change to your x value. Your x is your new domain. Your y-intercept, all y's change to x's. So you now have an x-intercept, and we swap out those numbers. And your asymptote, your y equals, your y changes to an x. Your asymptote becomes x equals 0. It becomes a vertical asymptote. So your log is an inverse of your exponential graph. And it follows all the right characteristics. All the x's and y's have to interchange. So does it make sense to you guys? Now, what also I want you to remember is when we did your exponential curves, they all work the same way. So this one was y equals 2 to the x. Y equals 3 to the x was a little bit here and a little bit sharper. The same thing happens with the log. Y equals 2 to the x will be a little wider when we convert it to a log. The 3 to the x will come here and just be a little bit closer to the axis. The one was closer to the y-axis, but now we switched them closer to the x-axis. Base 10, which is what your calculator does, base 10, will look like it's kind of stuck here and look like it really, really rides close. It does. If you think about it, 10 to the 1 is 10, right? And when we switch that, that's 1 That's your 10, your 1 and your 10. Your 10 and your 1 become 1 and your 10. So we swap those around. Instead of 1, 10, you're 10, 1. You're really tight down here. Now, your calculator has the same problem with your logs as it does with your exponential curves. If I just graph base 10 and logs, again, you know how your exponential curves look like it stopped along that over here? It stopped over here. This looks like it stops, but it really doesn't. If you do a value and you do 0.001, you're going to get a value for it. It just rides along that axis because that's where your asymptote is. Your calculator doesn't do it justice. Even when we do a transformation and we move it up, it still kind of just takes that little piece that they did and moves it up, even though the line continues to come down. So just kind of be aware of that because it had the same problem when it did your exponential curves. Everybody okay with this part so far? Makes good sense? As much sense as it can make on a Friday? Okay. We're just going to hit some of your transformations. All I'm hitting today is your graphing, your transformations. Now, your transformations work the exact same as they do with your parabola, your absolute values, but I gave you to see because sometimes with the log, they just look a little bit different. So if I take my log, I'll just use base 10 of x. So here's my log base 10. It works the same way. Has a domain from 0 to infinity, a range, all real numbers, x-intercept of 1, 0, and an asymptote of x equals 0. Now, if I take this and I do a vertical shift, if I do this, let's do a plus 4. It works the same exact way as before. When it's not next to the x, it's outside. This is your vertical shift up and down. So I'm taking this and I'm shifting everything up 4 units. Now before, when we did a vertical shift, it affected your range, didn't it? Because your range, you had a horizontal asymptote. The opposite happens. A vertical shift doesn't affect your range now because now it's all real numbers. A horizontal shift will affect it. It will affect your domain. It's the exact opposite of the exponential ones. So if I took this point 1, 0, and I moved it up 4, I'd be at the 1, 4. And I would be like this. See it? I didn't affect any asymptotes here. So your domain would stay the same, your range would stay the same, your x-intercept is going to change, but your asymptote is the same. Now, we're going to hold off on the x-intercept for a little bit, because for you to find an x-intercept, you have to put a y of 0. And we'll have to solve that log. So we'll wait until next week to solve that log. But just so that you know, these all kind of work the same way. If I do this one, and I start with log base 10, just a regular log, and now I shift it horizontally, it does the same as we did before. The horizontal movements now will affect your domain, where before they didn't, but we interchanged everything. We still go the opposite way, so we would go 2 units to the right. I'm going to go back to your original graph. So here's my original. Let's just make it a graph. Here's my original. 2 units to the right. Instead of 1, 0, I'm now at 3, 0. Instead of at x equals 0, I'm now at x equals 2. Instead of my range will stay the same. Instead of my domain being at this, I moved it to the right. My new domain is here. And my asymptote changed. Okay? So does it still make sense looking at your transformations? I just printed them out because I thought sometimes they look a little bit more confusing. where do you find them? You know, you just have to kind of move them around a little bit. The reflections work the same way. If it's the x that's negating, you have a reflection over the y-axis. If it's the y that's negating, you have a reflection over the x-axis. And that all will stay the same. A dilation, and we'll do just the verticals, they work the same. If it's greater than 1, it's a vertical stretch. If it's between 0 and 1, a fraction, then you took a fraction of it. It's a vertical shrink. A negative in front of this will have a reflection and a dilation. There's never a negative dilation. It's a reflection and a dilation stretch of by a factor of 2. Okay? So these are the same ones that we've seen before. And let's take a look at how we apply them. And we apply them and graph them the same way that we did. So again, you're going to give me your parent sketch. So your parent graph for this is your log base 10. And I don't know if you remember, but do you remember that if it's base 10, you don't have to say base 10? Base 10 is your default. So I don't have to put the base 10 in here. And that means base 10. That's what your calculator uses, base 10. So I start with my graph of my parent graph. My domain, my range, my x-intercept, and my x-asymptote. Okay? And what am I going to do to it? What transformation am I doing? To the right one. Good. A horizontal shift to the right one. I might want to keep track of this guy. I might want to put this up here. So now, when I move this to the right one, it becomes 2, 0. If I add 1 to that, my asymptote now becomes x is equal to 1. And what else is going to change? What else have I changed? The domain. The domain now, I'm going to add 1 to. So my new domain is 1 to infinity. My range is still all real numbers. My x-intercept, this one I can see because we moved it physically. And my asymptote is now x equals 1. And we say horizontal shift right 1 unit. That one doesn't change either. They're pretty easy, right? They follow just like we do the exponentials, but they're completely the opposite because we switched everything around. All your y's became x's, all your x's became y's. So they worked exactly the opposite. Alright, let's try one more. Now, just like when we did your exponentials, it's probably easier if you take this 2 and bring it out over here. It's probably easier to put it where you're used to looking at it. So your parent graph is your basic log. So we graph your parent graph. We start out with your domain, your range, your asymptote, and your x-intercept. And where are we transforming this graph to? Good, very good. Vertical shift up 2 units. So we're going to take that 1, 0, and we're moving the y. We add 2 here. We're at the 1, 2, and we just make it go like that. Did we change the domain? We didn't move across, so their domain is the same. Did we change the range? No. Any effect on the asymptote? Nope. But we did change the x-intercept. And the x-intercept we'll hit next week. The x-intercept, you can find it on your calc right now, but you'll need a log to find it. So we're going to hold off on that. The y-intercept we could find, but this is not going to hit your y-axis.